So I'm not using the water immediately. I form the bromonium ion. So that's my bromonium ion intermediate. Okay, so same principle as the bromination reaction. And now, of course, I have my counter ion, but I also have water. And so water, of course, you've already seen previously, on the right side here, water can participate in trapping carbocations, and the bromonium ion is just a very special case of a carbocation, where the positive charge actually, at least to a large extent, resides on ER. So we have several different reactions that this could undergo. Again, initially just an equilibrium reaction. And we have also a regiochemistry problem. So now you can go back to regiochemistry and look at the different properties. If we attack at either one of the positions of the bromonium ion. So now this is not a symmetrical bromonium ion. You can see previously I took some effort to select symmetrical bromonium ions, but now this is not selected symmetrical anymore, and so we have two different bond situations. So we have one bond, carbon-halogen bond, that is less hindered. And this bond is actually weaker because we have more of the tertiary carbocation. So this is a weakened bond. So two different bond situations. I can already see this bond that the way I drew it is already elongated because this carbon can accommodate the positive charge better than this carbon can up here. And so, in fact, the competition here, we have a lot of water, leads to water being the more successful one. So we have an excess of water. So water becomes the nucleophile. This is in excess, large excess. So we're actually breaking here the weaker bond. And we've seen actually something very similar in the opening of the epoxide. If you go back in your notes to where we introduced epoxides and oxalates for the first time, we have similar situations in acid-mediated epoxide openings. So there, this is an oxygen with a proton that reacts very similarly. So again, this is a parallel to some earlier discussions we had in the course. So then this species opens, and what we end up with is a bromine at the less substituted side, and we end up with the alcohol at the more substituted side. So again, this is the bromonium ion that is formed in this process, and this is the consequence of the bromonium ion opening, leading to regioselectively formed bromohydrin. So this is about halohydrin. Since I use bromine here, I get a bromohydrin product here, and the opening is regioselective. At the bottom, that is short, is elongated and thus also weakened in this process. So yet a variation on the addition of an XY group across a double bond. In this case, I add OH, and Br onto my double bond. Okay, any questions for the bromohydrin formation? So I could do this with Cl2, it would get a chlorohydrin. I can also do it with iodine. So iodine actually works here because we don't add two iodine atoms onto a double bond. You add one iodine atom and you make one carbon-oxygen bond. So this works for iodohydrin, also for chlorohydrin formation. But bromohydrin is probably the most common of these type of processes. Okay, any questions? Yeah. Yeah, so very good question. So this actually is the product after deprotonation. And so I'll write down the first intermediate because I abbreviated the mechanism to make sure that we stay on the same page here. This is actually what I get first. And then this species loses the proton. And I can use the Br minus, but more likely, of course, I'm going to protonate the additional excess water that I have. So water, H2O, will be my base. And that gives the product. So if you actually go step by step the mechanism, before I get to my bromohydrin, I would have this charge intermediate and then I lose a proton. Okay, so a lot of mechanisms. You're just going to have to work through those. That's why it's important that relatively soon you go back into your notes and you look at some of the details of the mechanism. And really, what you're starting out with, I would suggest, is the mechanism for these two transformations. That's why I would give them to you. Kind of go in there as soon as possible within the next day or two and try to figure out if you can get the same products that I drew here. So that's important in trying to understand, make sure that you get the key aspects of these mechanisms. And then once you can do that, I think the rest of it will become pretty straightforward. Okay, let's look at a different pathway now, and that is oxidation of alkenes. So in particular, the oxidative cleavage. And there are a number of processes. You can see from my projection now, we're going to look at the syn-hydroxylation, and because it actually is the stereospecific reaction, the hydrogen reaction, and then the potassium permanganate and ozonolysis type processes. But initially, we'll look at the hydroxylation of alkenes. So we start to oxidation with our alkene. So let's start again with cyclohexene and introduce one reagent that leads to dihydroxylation. So we'll actually start with a dihydroxylation reaction. Kind of the first process here. And for that we'll introduce a new reagent, and that reagent is osmium tetroxide. So osmium tetroxide, usually in the presence of some water, we'll see why in a minute, leads to a syn-diol formation. So this is again a very selective process, giving us access to the syn-diol via a suprafacial addition. Onto the alkene. And of course, we Again, this is a process where I draw one compound, but it's a racemic product, so I'll write down plus the enantiomer. Let's take a quick look at the mechanism. I'll do the mechanism of this board. So the key aspect is a very interesting new reaction. It's a cycloaddition of the osmium tetroxide, which is, by the way, a liquid, even though it contains this metal osmium, very heavy metal. And so this is an 2+4 cycloaddition in terms of electrons and 2+3 in terms of the atoms involved. So let me first draw the arrows here. And you can see that I'm attacking on the oxygens but shuffling electrons into the osmium, which has a very high +8 oxidation state. So the osmium oxidation state is +8. So it's very, very highly oxidized. And so it really welcomes those electrons that are flowing into the metal. That gives us what we refer to as the osmium ester. And this is a 2+3 cycloaddition. And just count the 2 here and the 3 atoms here. And they are in the cycle 6 electron sets. So we have a total of electrons involved here of 6. Okay. And so then the osmium ester is hydrolyzed with water, and that gives us our product by releasing the osmium from the system. So again, think about it. It's very similar to the sulfate hydrolysis that I gave you previously on this board. It's a very close related to what the other mechanism was, and it releases the diode. Okay, so we'll meet on Saturday, and I'll mainly focus on mass spec and IR. I do a little bit more here, but I plan currently to continue at this stage with the rest of the material of chapter 12 on Tuesday. Thank you.